Okay, so while she's setting up, I'll just introduce Adrienne and Lancelot, who's going to tell us about interaction equivalence.
Is the sound good? Okay, thank you. So I'm very happy to present this work today. I'm in my final year of PhD, and this is work done with my two PhD advisors, Beniamino Accattoli and Giulio Manzonetto, and also with a postdoc in our group, Gabriele Vanoni. So a central topic in the study of programming languages is program equivalence, and how do we check, how do we prove whether two programs are equivalent. So we'll focus on this talk in the untyped lambda calculus, and here, because of the syntactic nature of the lambda calculus, you can already build equivalences based just on the syntax and on identifying terms that are related because they have the same normal form, and possibly identifying them if they have the same infinite normal form. So this is a syntactic, a natural equivalence, but it is in general not enough. There are some programs that behave in the same way, but do not have exactly the same normal form, the same infinite normal form. So to deal with these, we have the notion of contextual equivalence that tells us when two programs are equivalent. So T and U are equivalent if in every context they behave in the same way. And what I mean by behaving in the same way is that they reduce to unobservable. So this notion of contextual equivalence really depends on what you want to observe. Usually in the lambda calculus, we consider a notion of reduction as an observable, and one of the most well-studied is head contextual equivalence, so where we set the observation to be having a head normal form, being in head normal form. And so this is because of the central concept of head reduction linked to solvability. So this head contextual equivalence is an equational theory, and what I mean by this are the 3 points: that it is an equivalence relation, that it is context closed, stable by context, and that it is also invariant, stable by beta equivalence. And so the first 2 points are really easy to see from the definition of contextual equivalence. The last point requires a bit more work. So if I move from this notion of a contextual equivalence where we only observe the result of a computation and try to also observe some things with the computation, I can, for example, observe the number of steps that it takes to compute. And so this is linked with the theory of improvement developed by Sands. And so here I will talk about the symmetric version, the definition of cost equivalence. And so cost equivalence is exactly this. T and U are cost equivalent if in every context they behave in the same way, meaning they give the same result and they give this result in the same amount of steps. So if we, again, go to the lambda calculus and we specify observation as head reduction, we will observe that two terms are head terminating in the same amount of steps. And so this is not an equational theory. It cannot be invariant by beta because beta will obviously change the number of head steps. So the starting point of our work is, can we mix both concepts? Can we have somehow a contextual equivalence, somehow cost equivalence that is still an equational theory? And so our idea is to be able to the internal dynamic of a program, but only count the interaction of the program with the context. And so this is the idea behind interaction equivalence. But how do we know what are the internal, what are the external steps, what are the interaction steps? And so our first contribution is to propose a framework to be able to really differentiate between these internal and external steps. And so this is, we call this the checkers lambda calculus, and I will introduce it a bit later in the talk. So this interaction equivalence is really this idea that we want two programs to be equivalent if they make the same amount of calls, the same amount of communication steps with the context. It will be an equational theory, and we have really, so we were heavily inspired by game semantics, and I think this is really reminiscent of the duality there behind, between context and programs. And this is also a bit related to how composition works in process calculi, in the pi calculus, and with label transition systems. And so we really want to count somehow the number of accesses, the number of resources that the program needs that are external to the program, so ignoring what's going on internally. So these contextual equivalences are really natural. They are really natural to define, and this is something that one could come up with easily. But these are really hard to check. There is this for all quantification on context. This basically means that you need to try your program for every possible input. So these are hard to check and hard to prove in practice. On the other end, there are equivalences that are very easy to check or easier to check, that are more intentional. So I gave, for example, here, Böhm-out equivalence, normal form by similarity, building the set of approximants of a program. But there are others. And so our second contribution is to be able to relate this black box principle, that is interaction equivalence, with actually an intentional equivalence, so Böhm-out equivalence. So this means that we will provide a proof method, that is, to check that two terms are interaction equivalent, you build the Böhm trees, and then you compare the Böhm trees. This is still not decidable, because the Böhm trees are infinite, and building the Böhm tree is not even decidable, but it gives you a proof method, and then you can actually check what are interaction equivalent programs. So this is also backwards on the other way, answering an open question in the lambda calculus that was, what could be a contextual equivalence that matches exactly Böhm-out equivalence? So now I'll go a bit more in-depth and actually present to you the checkers lambda calculus. So the usual lambda calculus is made up of two constructors and variables. So we have variables, and then the abstractions and application. And so we move to the checkers lambda calculus by duplicating somehow the two constructors. So we color application and abstractions with a tag, so either black or white. We keep the variables unchanged. And so we have a black lambda and a white lambda, and a black application and a white application. So we need to make explicit the application to be able to differentiate between them. And so the intuition is that you want the context and the term to be separated colors so that you know who is what is the context, what is the program. So let's paint the context all in white and the program all in black. But of course, this is at the beginning of the computation, and then you will compute and everything will get mixed. So how do we compute in this calculus? We compute, as usual, with beta reduction, but because we have colors, we have actually 4 variants of beta reduction, depending on the color of the lambda and on the color of the application. So we have what we call silent steps, where these are somehow monochromatic redexes, where the color of the application matches the color of the lambda. So that means that this is the program computing on its own, or the context computing on its own. And then we can mix these colors and have interaction steps. So when we have that the color of the abstraction does not match the color of the application. And so, for example, the first of these rules is somehow the program, that's in black, asking for an argument from the context. And so, yeah, the result of all these steps is, as usual in beta reduction, we just do the capture-free substitution. So this is the calculus, and we want to know where are the interaction steps, where are the silent steps. But of course, this is a calculus, and counting interactions will depend on the reduction sequence. So I give you here an example where we have the duplicator, the black duplicator, applied to an interaction redex. And depending on how we do the computation, we will either first reduce the interaction redex and then do all silent steps, or first duplicate the interaction redex, and that will mean that we'll have to do at least 2 interaction steps to get to the same result. So this calculus is confluent. We can always get the same result, but we will not preserve interaction steps for all the calculus. So that means that if we want to have a notion of interaction cost, we need to pick a reduction sequence. And so we pick the head reduction sequence, again for all this, for the fact that it is a central topic and really linked with solvability. And we consider the head interaction stock. So head reduction is deterministic. There can only be one number of head interaction steps. And so this notation means that T terminates with the head reduction, so T, a colored term, terminates in the head reduction with K interaction steps. So the number K only counts interaction steps. And so now that I have this calculus that is able to see what are interaction steps, what are internal steps, I can build a contextual equivalence that is somehow quantitative in that it counts the interaction steps. So we have T and U. So this is in the checkers world. This is still colored terms or tag terms. T and U are quantitatively, contextually equivalent if in all colored contexts, they have the same behavior in that the head terminates with the same amount of head interaction steps. And so this is the contextual equivalence, but a lot of the time when we're working with equivalences or relation between programs, we also want to introduce a preorder so that we don't have to do every proof twice. And so we say that U simulates T, not if they have exactly the same behavior in all contexts, but if U can do at least as much as T. So that in all contexts, when T terminates with K interaction steps, U will also terminate with K interaction steps. But we do not specify what happens when T does not terminate in that context, in a context. So the key point is that because we have been able to characterize what are interaction steps, what are silent steps, we can only count interaction steps. So we pull this back into the usual lambda calculus by just introducing interaction equivalence as we paint the program black, and then we look at what is the equivalence class in the checkers world. And so here the program will be all black, but the context, I said that they were colored contexts, they can have both black and white constructor. So this is the definition of interaction equivalence. It is an equational theory. It's really easy to see that it's an equivalence relation. It's context closed. Colored context are stable by composition. Invariance, again, is a bit more complicated, just because it's not easy in the first case. It requires some rewriting theorems. And the key point is that, of course, if I paint my theorem black and I could reduce it without painting it, it will still be a silent step. If it's all black, I can only do silent steps. So I told you about this interaction equivalence, but what are actually inequivalent or equivalent terms for this interaction equivalence? So the big thing is that interaction equivalence is not stable by eta equivalence. So eta equivalence is just T is equivalent to lambda x T applied to x, where x is not a free variable of T. And so this is an example of terms that are not interaction equivalent. So we have the identity and an eta expansion of the identity here named 1. And so we have a separating context, C, that is an all-white context that just applies two variables. And this distinguishes 1 and the identity, because when we paint 1 all black and we put it in this context, and when we paint the identity all black and we put it in this context, we do not have the same behavior. They both terminate, they both reach a similar normal form, but not in the same amount of steps, not in the same amount of interaction steps. One will make 2 interaction steps, and the identity only 1. Somehow these are different normal forms, but this is just because we added colors. If there were no colors, these would be the same normal forms. So these terms are usually contextually equivalent. So this means that the interaction preorder or the interaction equivalence strictly refines its contextual counterpart. So we are between beta equivalence and contextual equivalence, contextual preorder. We can actually do better. We can characterize exactly the interaction preorder by the preorder induced by Böhm trees. And so I have no time to tell you about the technical details of this proof, but what's interesting is that we use really well-known techniques and standard techniques for the theory of the lambda calculus, namely intersection types, which we paint in black and white, and the Böhm-out technique adapted to interaction, to the checkers lambda calculus. So when I told you about the definition of interaction preorder, maybe you would have expected something different, in that the interaction preorder just means that U simulates T, means that U can handle more cases than T, but when it handles the cases, it has the same amount of interaction. Whereas maybe you would have expected something along the lines of the interaction improvement, which says that U actually improves T. It can handle all the same cases, maybe more, but in the handled cases, it can actually do better. We could have that T in the context C makes K interaction steps, and U makes K prime that could be less than K. So this does not change the induced equivalence relation. We still have the same notion of interaction equivalence, but this is somehow about optimizing interaction steps. And so for this, we do not have a complete result yet, but we see that eta reducing terms may improve them because we are reducing the syntax of the term. But eta expanding them for sure will never improve a term. So as future work, we'd like to characterize exactly what is the interaction improvement. So we know that it's between the interaction preorder and contextual equivalence. And so because the interaction preorder is Böhm-out preorder, and the contextual preorder is Böhm-out with eta equivalences added to it, we think that it can match the Böhm-out preorder up to eta reductions only. So to conclude, we've introduced the checkers lambda calculus, that is a new framework to be able to tell what is an interaction between programs. And then we can define interaction equivalence, which is a cost-sensitive equational theory. And it is the first contextual characterization of Böhm-out equivalence without using effects such as non-determinism in the context. And in our opinion, it is quite simple. So for future work, we'd like to work this out in call by value, call by need, maybe revisit some of Sen's results, and also in effectful extensions of this calculus. A big question is, we were inspired by game semantics. This looks a lot like game semantics, but we have no formal relationship with game semantics. Maybe there could also be a relation with process calculi. And also, what does exactly this head interaction cost represent? We have no idea. I put here the keyword communication complexity because it looks like distributed systems talking to one another. But we have no expert on this topic in the authors. Thank you for your attention.
All right, I think we have time for one or two questions. Does anyone want to ask a question?
So this might be a bit a general question. So do you think that your result could improve practical decision of equivalence, of say Böhm-out equivalence, by some kind of co-inductive technique, for example?
Do you mean whether interaction equivalence could help in proving that things are Böhm-out equivalent?
Yeah, exactly.
No, I don't think so. Maybe it could help disprove things because it's usually easier to disprove contextual equivalence than for Böhm-out or this co-inductive definition. But Böhm-out preorder can be defined co-inductively, and you just have to build the Böhm-out or find the right simulation, and that's way easier than checking for all contexts.
So it's more on the negative side, where it could be of practical impact.
Yeah.
Okay. Yeah. Thank you.
Okay, could our next speaker come up? And I have a question for you as well. So in your syntax, in your reduction rules, you treat like a black lambda with a white application the same as a white lambda with a black application. Did you ever want to distinguish data going in and data going out?
I think that's an interesting question. That's something that people have asked me before. And we've not looked into this. I think this doesn't serve our purpose right now, but It might be interesting where we have like only communication going one way, or we only want the programs to be able to access film from the context but not talk to it back. This would be interesting, but we've not looked at it practically.
Okay, thank you.